Thank you, Chegorsh, and thanks everyone for coming to have a chat with me. And I thought that I'll try to keep it as simple as possible. I have been following the other talks in this session, and they have been exceptional. What I found was that in many cases, we have looked into the science in a very deep sense. The whole idea around energy harvesters for SHM came from the fact that in a lot of cases, we do get energy harvesting, we optimize it for the power, and then that eventual question comes in, but I mean, what to do with that power? Some people use it to power up other sensors. And one thing that we have been trying to take a look into is can we use the harvested energy, the signal of the energy, in a consistent way for health monitoring? And why do we think so? I am happy to discuss this later as well during the questions, that if you even feel that this is a new field or not. Do you think it's just simply old results put in a new bottle? But for me, what has been interesting is that, let's say you have a structure, any structure, and you want to know something about this structure. So in structural health monitoring, when I say monitoring, I mean that we want to see if something has suddenly changed, if something is changing slowly through various markers. We also would like to know that if where something has happened and to what extent. So these are the type of questions typically that are around SHM. Sometimes they're more difficult questions. We ask how much life is left in that structure. Sometimes we ask what is the reason behind that problem in that structure. These are harder questions. Eventually, I'm trying to see, okay, if there's a structure, there's an excitation onto the structure, and we sometimes know a part of it, but never the whole of it. We can't measure the whole excitation. We know some idea about it. There's some uncertainty about it, especially if it's a built structure. Then you can think of the structure as a filter, and what kind comes out from the other side is its responses, be it displacement, velocity, acceleration, strain. Next, we usually take those data and say something about the structure. With energy harvesting, the way I see it is, then it passes through a second set of dynamics, which is, let's say we have a say a cantilever type harvester at the end, and then the output acceleration goes into this cantilever, which is another set of filter, and it creates, for example, strain at a certain point where the harvesting material is situated. And then there's a third filter, which is the coupling of mechanical and the electrical through electromechanical coupling coefficient. And in low power, I mean, that constant, it varies a lot and things like that. It's dependent on the circuit that you have. But at the end of the day, you get the output as a voltage. Then you can pass it through a rectifier, or you can just keep it as an open circuit voltage, which we often do. So without the need of a lot of external energy, you still need two wires. We are now creating this dynamics which passes through the excitation to the structure, to the harvester's mechanical part, to the structure's electrical part. So in a way, the output voltage that we have is the dynamics of dynamics of dynamics. Now the question is how we can invert that back to the original behavior of the structure, performance of the structure, or the change of the structure. Not everything will be as efficient, but to what extent can we do it? Because if we can, it would be a really nice application of whatever harvesting that you do in many ways. And you only need small amounts of harvesting because it's not the amplitude, but rather the signature of it that would be relevant. So with that, I'm going to present a few results that we have. It's high on applications and it's low on the fundamental science. But we can, of course, discuss possibilities. Some part of it this is published, some part of it is unpublished, and some part of this is either we are working on it or we have thought about it, but we don't know how to go ahead with it. So any possibilities of ideas, collaboration, or criticism that Vikram, whatever you said, it just doesn't make any sense. Everything is welcome. But let's go through the presentation first. So I think what I'll do is today divide how we went through the idea. I just discussed that. Then we'll take a look at what we did with bridges, because it is a topic where we entered absolutely without any technological readiness, but we eventually implemented on full scale. So that's interesting. We looked into some SCOUR problems, which is a big problem right now in many infrastructure. We looked into pipe damage and leakage, and then also how it can be related to extreme responses and the design of structures and some future challenges. I'll start with the idea that irrespective of the exact values I've written in this slide, the projection, the market projection of structural health monitoring, it's actually really high now. People are thinking about it. People have understood the need to put sensors and make the structures more relevant to take decisions based on data. And it's increasing very sharply. With that, the vibration energy harvesting market is also growing really sharply. And this is actually a good time, I think, to investigate these kind of problems with its advantages and limitations. So in a way, the vision that I'm putting in, I'll tell you what part of that vision is a vision, what part is nearly like sci-fi to me right now, and what we have done. Although I've put in some logical sequencing to it from my side, I'll tell you what I've done. So essentially, analysis of harvesting signals to say something about the structure, that's something fundamental to this whole idea. So that's something we actually have done quite a bit. Then I think in some cases, getting detections in real time, it's actually very interesting. And we have now created an entire suite of first order perturbative, eigenperturbative techniques, which we think can be really relevant to the harvesting signals. But that arrow, the connecting arrow, it hasn't been dotted yet. In terms of system identification, we have done some basic works, but I think in terms like a formal inverse problem, a lot can be done, and it is required to be done if we need to take this more seriously than I have. Then only we would be able to create an energy harvesting based health monitoring framework. But the advantage is that if we do have it, we can move a lot of monitoring from powered to self-powered regime to a good extent. We have developed a lot of algorithms, so that has been developing independently, and it will keep developing. A problem, I think, with structural health monitoring is that if you read journal papers, everyone's method is the best method, and everyone else's is worse than theirs. This is a problem because I don't think in a lot of ways we have looked eye to eye to comparison and benchmarking, and that's something we need to do. So a good definition of what we are comparing, why we're comparing, what are the errors, that needs to be established in terms of evidence base, numerically and experimentally, so that we have a good way of comparison and we are comparing in fair terms. In future, we will see a lot of explosion around the electrosphere of sensors and IoT. There is a lot of work that can be done around the IoT, which we are in the process of applying for some projects. But last year, I think I went for 2 or 3 and none were funded. So maybe it's a bit early or not. I will touch a bit on the eco-friendly sensor side of things because a lot of harvester materials, they are lead based and they're not good for the environment, but there are other options that we can look into. And finally, as I said, like summer, like way outside our comfort zone, but we have started to looking into it. We won't go into details of that. Is eventually we can look into some harvester-based mechanical computing or analog computing, which can be really interesting for other application sectors as well. So let's go into some of the applications that we have been through with our approaches. The first one is bridges, which is obvious based on, in a way, my background, and also bridges are often far away. So if you have like self-powered sensors, that would be good. You put in something, then you forget. We were trying to figure out like if we can use, while the bridge is live, the interaction between the bridge and a vehicle, in this case, train, can we harvest the energy and say like, yes, it's consistent with the changes in damages? Because you can't have sensors everywhere on the bridge. If you could monitor every single point, you would probably get more information. But if it's acceleration based, you can only put it into a few places. So everything starts with, as I said, very low technological readiness, just the idea. And we started putting in models together. So one of the first things we did was we created models of real trains with their properties. So 071 and 201 loco are Irish trains, then the TGV, then the ICE, then the Japanese Shinkansen. We also had another one from Hong Kong, I think. And then we started moving these trains over a typical generic bridge made with finite element models, with rails and everything, with two trains passing each other, one train passing in various velocities. So, complete parameter study, along with the damage induced as a local area that has a stiffness that has been degraded. Why? Because if your model isn't right, I mean, of course, the bridge doesn't know that you're modeling it, but unless you have a fairly reasonable model, it would be very hard to do anything. So we did this full 3D finite element model, but also we also did some fundamental differential equation based models. So we know that even with our relatively simpler model, we get most of the behavior there. You can see the high frequency component are being missed in the differential equation model. And that gave us some confidence on the kind of results that we're getting. When I say differential equation based model, it can be as simple as, of course, many of these, like as simple as an Euler-Bernoulli beam with the damage represented like a very localized open crack without any width, but the crack section flexibility is now a polynomial of the crack depth ratio, which is the depth of the crack to the depth of the beam. And a harvester at a certain distance away from the damage. It can be far away, it can be relatively here, it can be here, and consider what the effects are as a vehicle goes by. So this is the simplest model of a vehicle. Why not a single point load? Because if you don't use a degree of freedom for the vehicle, you won't have the coupling between the vehicular degree of freedom and the bridge in terms of the surface roughness that comes in. So realistically speaking, we're like talking about a typical Euler-Bernoulli being example forced by a Dirac delta function represented by the vehicle, and consider the two beams on the two sides and consider the boundary conditions in between with the damage in there. And then you can always think of the load, which can be just the mass times its acceleration due to gravity, the weight, but then also the coupling because of the degree of freedom between the vehicular degree of freedom and the bridge degree of freedom and the surface roughness. So you see the vehicle goes past, and because of the Dirac delta function, it keeps on sampling whatever that's in the spatial domain into the time domain. And here again, it's the coupling. So which essentially renders the stiffness and the damping matrix time dependent. And then you have, of course, these are the types of surface roughness, from very good road profile to very poor road profile. And then for the harvester, the output of the bridge acceleration is now an input to the cantilever harvester here, which itself is again coupled with the first order electromechanical coupling with the system. So as I said, this is the excitation, this is the filter, then that's the output of the filter, which becomes now input to the system. But that again is coupled with the electrical equation. So really, again, we are looking at the dynamics of dynamics of dynamics. So once we get the results out of this, we found out, okay, what was the consistent patterns of train speed versus the power generated. Note that it's a fraction of a milliwatt. And once you have those things calibrated, you can then start talking about which speeds to consider. Because if it was one vehicle, you could get something in and around the peaks. But you now need to figure out yourself whether being in and around the peaks is more conducive to your detection. Because as I said, it's the pattern that's more important, not the amplitude. Because in and around the peaks, you'll get higher amplitudes, higher power, but it will be very sensitive. On the other hand, if you're on the flat part of the dynamic amplification, then small changes wouldn't, it would be more robust, but it would be less detectable. The power levels would be much lower. And at that power levels, the electromechanical coupling is more uncertain. So there is a trade-off here. What was good was that if we looked into the experimental data, and we got the experimental data from a bridge in Sweden, we looked into PZT and PVDF, polyvinylidene fluoride and lead zirconate titanate type harvesters. There was a consistent degradation or a consistent change with the power generated versus the trains. And in small scale model, lab-based model, we also saw some consistent trends. So idea was, okay, we can now match our simulated measurements with the typical bridge model, so the bridge is listening to us. Can we go a little further than this? So with that, what we did was we started thinking about how to put those sensors into bridges. And as you know, most infrastructure, it's very hard to get permission to go in there. But what's interesting is in most bridges, the accelerations that you see, they tend to be definitely less than half a G in most cases. And also the amplitude of displacement, they tend to be only a few millimeters. So now think of your any standard electrodynamic shaker in a lab. They typically go between, say, it says 0 and 200 hertz, but at 200 it heats up a lot. But somewhere within these kind of frequencies that we are looking into, the typical amplitude and the acceleration, they can all be exactly recreated. So you don't have to go to the bridge and experiment something. The bridge comes to you and gets the experiment done, even if it was measured maybe 10 years back. You take those numbers, you exactly recreate the whole thing in the electrodynamic shaker. On the Stinger, you have a small accelerometer and you make sure that your accelerations are making sense. There's a bit of craft to it. You need to play with the gain a little bit before you get the right thing. But then you can match your theoretical and experimental accelerations and also your harvested energy voltages. Not as much, but it's not too bad. So the question is, what do you do with those measured voltage to find out a consistent change? So we did this for various kinds of trains. Say this one is for 201 Loco in Ireland. That one is from ICE. You can consider what the ride quality of a person is, what kind of acceleration that comes to the bridge. So a lot can be done. Next, if we started taking just a basic Fourier transform of these things, but that was obvious, the location of the frequency, they matched quite nicely. So at least in terms of changes in fundamental frequencies and those kind of things, it's good because now we have a project called CIRMA where we are instrumenting a train with various sensors, and we are making it go all around the network in Ireland and considering the moving train as a moving sensor on your network. So it was a good background idea behind it. So as I said, of course, the theory and the experiment for these things, they should and match well, and they did match well. I think it's a poor form on my part to put 3 decimal places in frequency after the decimal places. That's purely from just computation, so you can ignore that. Just think of the first decimal place, and that's good enough. Then the question was like, okay, we have done all these things. We have exactly replicated it in a lab. Can we now implement this in real bridges? Because we had the harvesters made, we had it experimented in our lab. Now the idea was to put it in real bridges. So we had 6 of them, and we put it up again, another bridge in Sweden. And what was being done was, while this entire bridge was live and trains were passing over it, we were shaking this bridge up and down as a chirp. So first in increasing frequencies up to 150 hertz, and then in decreasing frequencies, and many, many rounds of it while the train passes over. So it's a very exciting experiment overall, as you can think. And then we had accelerometers and harvesters side by side to see, okay, is it making sense? You see, this also gives another idea. And as I said, I'll discuss some of the ideas which we haven't done, but I'm happy to discuss this, and we are actually working on it now. So typically from one location, you have these outputs, but if you have an energy harvester, let's say 2 different things, one is piezoelectric, one is electromagnetic, then you have the same data filtered by 2 different physics, giving you 2 different outputs at 2 different levels. So now, if you could, for system identification, solve the inverse problem nicely, rather than one equation for one output, you now have 2 equations. So each time a new physics has been putting at the same point as a harvester, it's like giving you an extra equation about the structure. So that's something quite interesting and exciting to work with. But anyway, long story short, that was the type of harvester that we made. And so you can see the piezoelectrics here. Those masses could be changed along this groove so that we manage its natural frequency. We kind of had an idea about the range of natural frequency. So we put the central frequency and then had the, essentially we distributed the 6 frequencies of the 6 harvesters on the left and right hand side of the first bending frequency that we found from finite element modeling and the differential equation based modeling. So all these previous steps were done. And the good thing is that we actually found the passage of trains quite nicely picked up from even when there was an external excitation going on. So each of these things, those are from accelerometers, whereas this is from the voltage. It creates a change as the train moves over these kind of bridges. So for axle detection, for detection of changes, it can be nice. Again, just by taking either something really simple like the Fourier spectrum of the harvested voltage value, or just taking a look at the time series or just the scaleogram of the of various modes, we could start seeing like, okay, if there were modes, we did some EMD as well, they were close by or not close by, and then compare it against our models. We did not have a distributed number of accelerometers, so there was not a possibility to get the actual mode shapes extracted from them, which in hindsight is something that we should have done. But again, we could separate out within certain times what might be the modes, and that was useful as well. Then there were some statistical techniques on the harvested energy, because once you have the energy, you need to do something about it to create markers. And we saw that we had an energy operator define the kurtosis of it, or just the kurtosis itself. They could give you like kind of like, in a way, a significant difference which can automatically tell you when a train passes over, and the depth can tell you what might be the relative axle weights. Again, it was the same thing with some recursive techniques that we found out for like finding out exactly at what instant the train passes over. But these are really about anomaly detection, and any method that you use can work. This is just an example to show it's consistent. You can use harvesters for these things. The next problem that we focused on was on SCOUR, because bridge SCOUR is a massive problem, and a lot of bridges get washed away, or they're the legs are scoured away and they fall down and you can't do anything about it. I've been involved with some of those bridges as well. One around its after it fell down, and one because it got washed away. So what we did was, this was in collaboration with Kyoto University in Japan. This is an experiment done in Japan. So we created these like multi-span, small scale bridge vehicle interaction model, and we had the vehicle moving in various speeds controlled, but we controlled the scour by changing the stiffness of these boundaries, because that's overall, you can say that's what happens. Of course, there's a stiffness loss in the rotation as well, but that was not in consideration here. Only the vertical stiffness, they were being changed. And then we had the accelerometers, but you also had, with the accelerometers, energy harvesters coming out from them, very similar to what I just showed you before. You can see there's one coming out from here with a tip mass, and there's this energy harvester. So, and there's vehicle tracks on top. So we carried out many of these experiments with a model vehicle, and you can see it has the lower degree of freedom and the upper degree of freedom with specific string stiffnesses, and they were all calibrated and checked, and also the bogies between them, they have their articulation as well. So if we divide their forced and free vibration separately, we could find out quite nicely the electrical noise, the harvester frequency, and all the other main frequencies coming out of it. And then it was a matter of going back and checking against the models which ones were right. Now, you would be absolutely correct in saying like we wouldn't have the models all the time, but that's a difficult question, and I wouldn't know if we have a reasonable model how to distinguish like the right the right frequencies in some occasions. However, what was obvious is in these pairs, if you look into these pairs, if you go for 25% or 50% of stiffness loss in these pairs, you might say like, oh, that's actually big. They are big, and when they happen, they're big, and that's when you really start making changes, but you wouldn't know visually when they're changing. So either way, you would need a sensor there. And an energy harvesting sensor might be good because it changes the energy pattern, and it also changes the shift in frequencies in between healthy and unhealthy structures. We in fact did the same. I didn't put this slide here on a concrete beam with damage. I didn't put the slide here because our input method wasn't good. We didn't have control because we hit it with an impulse hammer, but we didn't have a lot of control on that impulse. But there again, we saw a consistent distortion and change in the frequency between damaged and undamaged. So something like this can be done very easily just from just by using the harvested energy patterns. So as you can see, we can take a look at these kind of changes, and they're consistent. This is not an like each would be like an experiment, because we had to excite them separately, and then again here these were because of the vehicular interaction. In some people say that the free vibration is a much better way to get these frequencies out. I would say like yes, yes, but if the signal is nice, sometimes it's just too variable. So even though if you just take one, you get a nice peak, you take the next one, you get a shift of the peak, and then you're thinking like, okay, do I just now draw a distribution of the peak or take an average, what to do around it? So again, it is there has to be a balance. So at least one thing we know is that if there is, and we used the Moholy-Nagy distance squared here just to as an indicator, you can take like whatever that works. But one thing we can say is like that there is a significant difference that can be identified by energy harvesters for scour problems, and it's consistent with the change with the amount of scour. You might say like, okay, you've only done 25 and 50%. Why did you not do the values in between. I think we should have, but we couldn't because we ran out of time. The person who was there had to come back as well. But yes, in between, if you get those points, you'll probably see a very nice curve, a monotonic curve forming, and that's what we would like to know. That's interesting. Then we also looked into a bit of pipe damage because pipeline is becoming very important. You'll see like pipelines, even with the United Nations challenges around water, it includes pipelines as a major challenge. Even in Ireland, about 40, sometimes quoted values are 50% of water that's lost due to leakage and or damage. I was looking into some reports in Brazil, and in some places in Brazil, it's as good or as bad as Ireland. In some places, it's even up to 75, 80% that's lost. Then the idea was, okay, can we see whether we can detect consistently pipe damage or not? And this was done in Rice University in Texas. This is probably the simplest of all, but this is to demonstrate it can also be very simple. We just slapped in some PVDF patches all around, but modeled those damages with a nice 3D finite element simulation. And we excited with a motor with an imbalance at various frequencies and tried to figure out what is the harvested energy picking up. You might say, well, this is just a glorified version of strain, because it is the strain that the harvester is picking up and it's creating voltage. That's right. But if you put in a strain gauge, for each strain gauge, you'd have to now need to have a reference voltage sometimes. And with a harvester, this can be very flexible in terms of its application, and you probably can cut down on not just the external power, but also the wiring, the instrumentation part of it a whole lot. And when this is not in a lab, it's far away somewhere, it does make a lot of difference. What we found was that even with two damages along the length of the beam separated to a certain degree, our power outputs could pick it up. What happens if those two damages come closer? Well, they then behave as one damage and you can distinguish them, but still you know not just the presence and the location, but also the severity of the damage through this way. Again, this is another example of experimentation. You can see, like, yes, the strains do respond to it as we expect, and it creates a peak when a single damage is present. Here, we took a look at the voltage that's being created by the damaged location here versus how quickly it drops off to the next location. And as you expect for strain-based damages, there would be a sharp drop-off of the voltage. This part is where the excitation is close to the resonance, not the resonance, but excitation is close to the value of the first natural bending frequency of the pipe. And then the other ones are lower. But you can see how fast the whole thing drops. So there's a thing around how sharp it can detect something versus how stable the whole thing is. That is something that would always be there. We also saw that the voltage, of course, is picking up the beating phenomenon when the excitation and the beam natural frequency is coming together. And that's something good. That's something interesting because it can distinguish between close frequencies, and in the frequency domain, we're actually getting quite clean signals, so to say. From there onwards, then we also went to look into pipe leakage. And for pipe leakage, one of the things we found was that there was no experimental evidence base or database to look up to see whether an energy harvesting works or not. And here we worked by creating a benchmark pipe rig as well. So for the benchmark pipe rig, we controlled the flow, we controlled the damage on the pipe, and we also controlled the leakage on the pipe, and that's the pipe section. So that's how it looks like. So this is the pipe section. You can have damage and leakage on this. You can see that the gauges are here controlling everything. There's also a pump, and we control the flow rate as well. So that gives us control on maybe not on the total amount of turbulence, but at least on the flow rates the amount of damage and how the water flows through it. So the water flows through it, of course, it creates some kind of a vibration strain on the pipe. And now the question is, as the leakage increases, is it consistent? As the damage increases, is it consistent? And would increase on that leakage and damage, would it be eaten up by the variability of the flows, or would it come up as a phenomenon that is stronger than those things? So that's the big question. And what we say is like, yes, that's actually correct. Even if you look at the raw data, right from the healthy state to a 3 millimeter leak state, which is essentially you cut in a 3 millimeter width with a saw in the pipe and it starts leaking, versus 7 millimeter leak state, you can see that yes, I mean the at least like it's a wider fluctuation of your voltage, and again the voltage signature gives you an idea about the leakage. If we look at the various pipe states, right from 2 to 10 millimeter leak state, we can see that for the 7 like gallons per minute, we should have done it in liters per minute, but like 12, 15, 19, and 24 gallons per minute, we can have very nicely calibrated graphs that show what the amount of leakage is for the voltage for each of the sensors put in there, which is quite like heartening to see. Again, we just said like, okay, because they didn't start from zero, can we just make a simple leak index? Just subtract the baseline from what we see and divide it by the baseline and see what amount of change there is, so that we can compare the various vertical axes together. I mean, don't even treat it as an index or something. It's just making everything go back to zero when we start. It's a very consistent increase of leakage detection for various flow rates. So all you need to know is like ballpark what the flow rate is, and they're well separated out. It's not being eaten up by noise and fluctuations. Then is again the interesting part. We haven't published it yet. We are it's been sent. A lot of these are made out of like lead and things like that. What about other methods, other materials to look into? One of the things that we've been looking into is biosoluble, biodegradable crystals or harvesters. If we can use it on structures, that could be something really interesting. And so we have now like worked on harvesting energy harvester sensors made of protein crystals using gamma glycine. And with the gamma glycine, the problem is we know it creates harvesting energy, but it's extremely like it fluctuates a lot. You can't just like buy it. You have to create it in the lab. You have to deposit it, and then you kind of like create a patch and start seeing, okay, is this making sense now, or these new materials they're not going to work at all. So that was a very long piece of work with a lot of frustration, but now it works, and I'm really, really excited to show it here. Because first of all, I mean, we have now a sensor created that makes sense. We have its thickness, capacitance, piezoelectric, like strain constant more or less sorted out. You'll see that there's an empty bar here at the modulus of elasticity, because it's still not obvious. It gets brittle very quickly. But again, that's something that we could look into. And what we did was like use the same test rig, but also use damage and also leakage. And by leakage, before we were like, okay, there's a constant leakage of water coming out. But what if there's a sudden leakage, and how can we detect the portion, and can we also detect where it leaked, and is it consistent with the amount of leakage? So for that, we made this kind of a like stopper, and while the water is flowing, we suddenly pull it out and see what happens to the harvesters themselves. And there has been no application of these kind of gamma, like protein crystal type harvesters for any application. So it's actually really exciting to see that it has an application in structural health monitoring. So if we go through this, we have been to a number of like flow rates of the pipes, and for various leak states, that we go through. And we have carried out an extensive range of experiments, and we have numbered like all these pipe states, so 20 types of pipe states, and we have done these tests many, many, many times for low flow rate, high flow rate, and things like that. What we see is really interesting is that as compared to the baseline, which is in red, the blue very consistently shows in terms of its sudden change, its amplitude, and its variability when a certain leak happened. Not only that, to what extent it happened, and the gamma glycine sensors, they are turning out to be a really good way to indicate and detect these kind of leakage and damage properties. We could compare it with like a number of various types of flow rates, and we can see it being consistent. We can also compare it against each other, and we also see that it is consistent in terms of the voltage that they are creating when the same amount of damage is present for the various types, like various numbers of pipe state that we consider. Then also comes like in terms of the abrupt change, can we find out even just from the voltage that's being measured and log it somewhere to know where the whole thing happened. And it's precisely giving us very nicely where such changes took place. So just by logging them, you can find out at what point somewhere in a pipe something went wrong. What's the challenge? The big challenge is like, okay, how do you go underneath? How to get access to a pipe and put them in? What are their durability? Are they going to completely get off the scale if there's humidity and other aspects? We do not know the answer to that. And currently we are working on some aspects of it. But again, I mean, if it would be good to see what other options are there. I'm aware that I only have a few more minutes, but I might just show you one other thing, because all these things are detection and all of that. But let's say not always do we see sudden changes. We just keep on getting data sets and data sets and data sets. Can we use it, and to what extent can we use it? Here, what we happen to show is like, it's interesting. In a lot of cases, when we design for a structure, we design it against a return period of a certain natural hazard. It can be an earthquake, it can be wind, it can be waves. And those are based on the histograms and the response histograms of the structures because of the excitation of the hazard. And we tend to pick something at the tail of this histogram and say, well, at that probability in a standard normal space, we now call, okay, this is the design value, and we are making our structure safe for this. And then we call it like, okay, in that space, it is equivalent to based on a certain model, let's say Gumbel distribution or something. It corresponds to a 100-year return period. We call it a 100-year storm. But eventually, it is like getting to estimate the tails of the distribution quite well. So if a wind acts on a structure and we keep on getting all these data constantly being logged rather than throwing it away, we can possibly start fitting a location-specific distribution and start estimating what might be the extreme responses of whatever structure is there at that point, and it might give us some extra years out of it, because it has been previously shown in various structures that if you do a structure-specific load distribution, in many cases, not in all cases, but in many cases, it shows that the extreme responses originally designed was overestimated by 10 or 15%, and that's actually law. So this can actually be done for various kind of situations. We showed it for wind, and we also showed that for various wind risk spectra that are considered, say, here's a comparison between Kymel and Davenport spectra. Can we map the return levels of extreme events from the voltage? And yes, we can. We can correspond it to the standard, bog standard first and second order reliability methods, and also the fragility analysis of these structures. I know I'm slightly, I think I'm now getting out of time, so we can discuss that later, but we can show scenarios, and this can then be showed, I think energy harvesters can then be linked to possible climate change or climate variability effects, maybe not change, but effects of natural hazard at a certain location, and it can be very good against various demands of structures. So we can create fragility curves out of it, and we can also then compare certain design options one over the other. In future, I think I'll take no more than a minute or two. In future, I think one of the big challenges I think would be around the hardware on where you have these harvested values of energy. What do you do with it? Still, it's like all we have done is we have taken the open circuit voltage and have explored it. A lot can be done. A lot can be sent to small like sensors, sensor networks. What kind of indicators can we send to a cloud or wherever? To what extent can we carry out computation locally within a structure? All these are like relevant, interesting, important questions, and we probably need to get answers out of them to get the best out of structural health monitoring. We need a lot of benchmarks and examples because, as I said, right now, one of the problems with this really exciting field is everyone's method is the best, no one's method is the second best. So we need examples for that. But we have done some work around this, some work around harvesting energy and how we can do intelligent power supply to other small sensors. But it's still at a very, I would say, at a very basic stage as compared to someone who works directly on electronics hardware and things like that. We have been looking into other kinds of, say, solid solution crystals as well, and see if they can be used for health monitoring. For example, you can have multifunctional perovskites, and they possibly could have some aspects about having monitoring from different levels. So in terms of data fusion, or even taking like 3 different physics, creating 3 different signals for the same output, it can be quite interesting. Just like I said, the combination of piezoelectric and electromagnetic. You get 2 equations instead of 1. And we do see that for an oscillation, we get open circuit voltage. I'm not showing any more on solid solutions on multifunctional perovskites because we're still not getting very consistent results in terms of damages. It does show there is a change, but it has to give you ballpark the same results every time. Maybe it's got to do with packing, maybe it's got to do with the manufacturing, but I am not a material scientist and I don't know. I'm coming to that question, Christina. I'll keep that in mind. A big question will be how we can take just the outputs and ballpark estimate what might be. It may not be the reality, but the best estimate of a system just from the outputs in between linearity and nonlinearity and determinism versus stochasticity. It's a big problem that we're looking into. New kinds of harvesters and new kinds of harvesters, plus in a lot of cases, various harvesting signals, they can be combined. And as I said, the sci-fi part of it is they can possibly create logic gates and some amount of analog computing, which we have looked into to some extent theoretically, but not experimentally. So as a conclusion, energy harvesting technology, I think it has a future for SHM, but we need more use cases and evidence bases. That's the key, and fair comparison of performance. New materials and communication methods, it can really lead to disruptive advantages and make it as a serious player in this field. And novel algorithms for detection, it must be tailored specifically to energy harvesting. You can't just take an SHM method and add it to your harvested signals and get results out of it. It does not work well. So with that, I think I must thank you for your attention. This is not, as I said, it's not my work alone. You can see a range of people that we have worked with and are still working with. We've been funded by the Atlantic Area CIRMA project, the Martera Eranet Co-Fund project, JPI Oceans, the Science Foundation Ireland, and the Irish Research Council. We are supported actively by Marine and Renewable Energy Ireland and the UCD Energy Institute. So with that, I would like to thank you and come back to the questions. I think I already have the first question sent to me, but thanks a lot for bearing with me for this time. Thank you.